my name is Tommy. Today we're looking at intermolecular forces. So determine for each measurement if it is inversely or directly proportional to IMFs. So boiling point and melting point both increase with intermolecular forces because the stronger the intermolecular forces, the harder it is to pull the molecules apart, and therefore it increases with boiling point and melting point because it requires more energy to rip them apart and to become liquids or gases. So heat of vaporization and fusion is the same thing as boiling point and melting point. The more IMFs you have, or the stronger they are, the harder it is and more energy required to tear them apart. So it goes right under them. Viscosity, or how hard something flows. Something with a very high viscosity is like syrup or honey will not flow very much, and it has a high viscosity. So viscosity increases with high IMFs because, again, those molecules are pulling on each other and kind of keeping themselves from moving away from each other. Something with a very low viscosity will flow very easily and thus not have very high IMFs. So it is directly proportional to IMFs. Vapor pressure. So vapor pressure is if you have a liquid in a container, how much pressure does the gas above the liquid exhibit? So it's going to be inversely proportional to IMFs, because the stronger those IMFs, the less likely that liquid's going to evaporate to form a gas. And if it's less likely to form a gas, then there's not going to be as many collisions occurring and therefore less pressure. So vapor pressure is going to be inversely proportional. Volatility, or just how much something evaporates on its own, is going to be inversely proportional to IMFs for the same reason as vapor pressure, because the more IMFs you have, the less likely it's going to become a gas, and the longer it's probably going to take to become a gas because those molecules are tugging onto each other and making sure they're not really moving that much. So volatility is inversely proportional. Surface tension is basically how strong the surface of a liquid is, how hard it is to break. And surface tension is directly proportional to IMFs, because think about it, the stronger the molecules are holding on to each other, the harder it is to puncture through them, if that makes sense. So those are the measurements, and whether or not they're directly or inversely proportional to IMFs. For this problem, we have to consider why the boiling point of CS2 is higher than COS. CS2, we can see, has a higher boiling point and is non-polar. So all it has in terms of IMFs is London dispersion forces, which all molecules have. COS, on the other hand, is polar and has LDFs and dip-dip, or dipole-dipole, because it's asymmetrical. So why does CS2 have the larger boiling point? Well, when you see this, and you see that the one with the lesser amount of IMFs has a higher boiling point, that's because that one IMF is greater than the other two combined. So the LDFs of this outweigh the LDFs and dip-dips combined of COS. And that's because this, CS2, has a higher molar mass, has larger atoms in the compound, and is thus more polarizable, or the electrons can more easily shift and cause greater London dispersion forces, thus causing the greater boiling point. For this problem, we have to identify which compounds participate in hydrogen bonding. So before we talk about this, hydrogen bonding is by far the strongest IMF, and it's a special dip-dip force, and it occurs when and a very electronegative element takes away an electron from hydrogen, effectively causing hydrogen to just become a lone proton. And that lone proton can interact with another highly electronegative element and cause a very significant dip-dip interaction, causing very high IMFs. So the only electronegative elements that cause hydrogen bonding is N, or nitrogen, oxygen, and fluorine. So let's take a look at carbon monoxide. We have carbon and we have oxygen, but no hydrogen. So carbon monoxide is not going to cause hydrogen bonds. H2O has a hydrogen bonded to an oxygen. So H2O will exhibit hydrogen bonding. Ammonia, or NH3, has nitrogen bonded to hydrogen. So yes, this will exhibit hydrogen bonding. HCl will not exhibit hydrogen bonding because hydrogen is bonded to Cl and not NOF. So no, I would not exhibit hydrogen bonding. Hydrofluoric acid would have hydrogen bonding because hydrogen is bonded to fluorine. Now, it is good to note that hydrogen and fluorine may both be in an element, but if they're not bonded together, then hydrogen bonding would not happen.